Question 1. If L vector is the orbital angular momentum operator and sigma vector are the Pauli matrices, which of the following operators commutes with sigma vector dot L vector? Option A, L vector minus h cross by 2 sigma vector. Option B, L vector plus h cross by 2 sigma vector. Option C, L vector plus h cross sigma vector. Option D, L vector minus h cross sigma vector. Solution. Since S vector equals to h cross by 2 sigma vector tends to sigma vector equals to 2 upon h cross S vector. Therefore, sigma vector dot L vector equals to 2 upon h cross L vector dot S vector. Now, the total angular momentum J vector equals to L vector plus S vector equals to L vector plus h cross by 2 sigma vector. Now, the commutator of J vector comma L dot S vector equals to 0. So, the option B is correct. Question 2. Quantum particle of unit mass in a potential V of x equals to half m omega square x square when x greater than 0 and infinite when x less than equals to 0 are in equilibrium at a temperature T. Let N2 and N3 denote the numbers of the particles in the second and third excited states respectively. The ratio N2 upon N3 is given by option A exponential 2h cross omega upon kBt, option 2 exponential h cross omega upon kBt, option 3 exponential 3h cross omega upon kBt, option 4 exponential 4h cross omega upon kBt. Solution. The energy eigenvalues of a half harmonic oscillators En equals to bracket n minus 3 by 2 h cross omega, where n equals to 0 to 4, and these eigenvalues are non-degenerate energy levels. Now the number of particles in an energy level are Ni equals to Gi exponential minus Ei upon kBt according to Maxwell's law, where Gi is the degeneracy of ith level. Thus, N2 upon N3 equals to G2 exponential minus E2 upon kBt upon G3 exponential minus E3 upon kBt equals to exponential E3 minus E2 upon kBt equal to exponential beta bracket 11 by 2 h cross omega minus 7 by 2 h cross omega equals to exponential 2h cross omega upon kBt. Option 1 is correct. Question 3. A quantum mechanical system is in the angular momentum state L equals to 4, Lz equals to 4. The uncertainty in Lx is option A h cross square root 2, option 2 2h cross, option 3 0, option 4 h cross. Solution. Let us find expectation value of Lx. Get Lx equals to state L equals to 4, Lz equals to 4, Lx 4 tends to where Lx can be written in lowering and raising operator. The Lx expectation value equals to 0 and variance of Lx is equals to Lx square equals to Ly square equals to half expectation value of L square minus Lz square equals to half graph 4 plus 1 into 4h cross square minus 4h cross whole square, which is equal to 2h cross square. Hence, the uncertainty in Lx equal to del Lx equals to square root Lx square minus Lx square equals to h cross square root 2. Hence, option 1 is correct. Note, the L square operates on L, M states gives the value LL plus 1 h cross square, and LZ operates on the eigenvector L, M, which gives M h cross L, M. Question 4. A single particle can exist in two states with energy 0 and E respectively. At high temperatures, kBT greater than E, the specific heat of the system Cv will be approximately option 1 proportional to 1 upon T, option 2 proportional to 1 upon T square, option 3 proportional to exponential E upon kBT, option 4 constant. Solution. The partition function of the system Z equals to summation over Gi exponential minus Ei upon kBT, which gives Z equals to 1 plus exponential minus E upon kBT. Now the average energy U equals to summation over Ei Pi, where Pi is the probability of getting the ith energy level, equals to 0 into probability of getting the energy 0 plus energy E into exponential minus E upon kBT upon Z. The specific heat of the system Cv equals to du upon dt equals to E exponential minus E upon kBT upon Z bracket E upon kBT square plus E minus 1 upon Z square exponential minus 2E upon kBT bracket E upon kBT square in the high temperature limit is equal to 3 by 4 E square upon kBT square, which is proportional to 1 upon T square. So option 2 is correct. Question 5. A body of mass m is acted upon by a central force F function of r equals to minus kr vector, where k is a positive constant. If the magnitude of the angular momentum is L, when the total energy for a circular orbit is option 1 2 square root kl square by m, option 2 half square root kl square by m, option 3 3 by 2 square root kl square by m, option 4 square root kl square by m. Solution. Given the central force Fr equals to minus kr vector tends to Vr equals to integration minus Fr dot dr equals to kr square by 2. The total energy E equals to kinetic energy plus potential energy equals to mr dot square by 2 plus L square by 2 mr square plus kr square by 2 equals to mr dot square by 2 plus V effective. For the circular orbit, the derivative of radius equals to 0 and derivative of effective potential equals to 0. Thus, derivative of effective potential 0 at r0 equals to 0 tends to minus L square by 2 mr0 cube plus kr0 equals to 0 tends to r0 square equals to square root L square by mk. Hence, the total energy for circular orbit E equals to V effective equals to L square by 2 mr0 square plus kr0 square by 2 equals to square root kl square by m. Option 4 is correct. Question 6. Two non-interacting classical particles having masses m1 and m2 are moving in a one-dimensional box of length L. For total energy not exceeding a given value E, the phase space volume is given by option 1 pi L square E m1 m2 upon m1 plus m2. Option 2 pi L square E square root m1 m2. Option 3 2 pi L square E m1 m2 upon m1 plus m2. Option 4 2 pi L square E square root m1 m2. Solution: the total energy of the system E equals to P1 square upon 2m1 plus P2 square upon 2m2. Since potential is 0 in the box, so this equation is an elliptical equation. So the phase space volume for non-interacting particles equals to summation over two particles dx1 dx2 summation over two particles 2p1 to p2 equals to L square, which represent the area and volume in Cartesian space into volume in momentum space equals to pi square root 2m1 E square root 2m2 E equals to 2 pi L square E square root m1 m2. Note: area of an ellipse equals to pi a p, where a is semi-major axis, b is semi-minor axis. So option 4 is correct. You can see the figure. Question 7. The Hamiltonian for a one-dimensional simple harmonic oscillator is given by H equals to P square upon 2m plus half m omega square x square. The harmonic oscillator is in the state psi cat equals to 1 upon square root 1 plus lambda square bracket 1 cat plus lambda exponential iota nu 2 cat, where cat1 and cat2 are the normalized first and second excited states of the oscillator, and lambda and nu are positive real constants. If the expectation value of x equals to beta square root h cross upon m omega, then the value of beta is option 1 upon square root 1 plus lambda square. Option 2 square root 2 lambda cos nu upon 1 plus lambda square. Option 3 2 lambda cos nu upon 1 plus lambda square. Option 4 lambda square cos nu upon 1 plus lambda square. Solution: the expectation value of x equals to psi cat square root h cross upon 2m omega operator a plus a dagger, where a is towering operator, a dagger is raging operator, equals to square root h cross upon 2m omega bra psi a plus a dagger 1 upon square root 1 plus lambda square bracket state 1 and state 2 equals to square root h cross upon 2m omega bracket 1 upon lambda square plus 1 or 2 bracket cat 1 plus lambda exponential minus iota nu cat 2 bracket lambda 0 plus 2 lambda exponential iota nu cat 1 plus square root 2 state 2 plus square root 3 exponential iota nu state 3. Expectation value x equals to square root h cross upon 2m omega 1 upon 1 plus lambda square bracket square root 2 lambda exponential minus iota nu plus square root 2 lambda exponential iota nu. Taking the common square root 2 and lambda, we get the cos formula in exponential terms. So option 3 is correct. Question 8. A set of 100 data points yields an average x equals to 9 and a standard deviation sigma x equals to 4. The error in the estimated mean is close to option 1 3.0, option 2 0.4, option 3 4.0, option 4 0.3. Solution. The error in the estimated mean is given by delta x equals to sigma x upon square root n equals to 4 by square root 100 equals to 0.4. Option 2 is correct. Question 9. A hydrogen atom is in the state cat psi equals to square root 8 by 21 cat psi 200 plus square root 3 by 7 cat psi 210 plus square root 4 by 21 cat psi 311, where cat psi and LM are normalized eigenstates. If L square is measured in this state, the probability of obtaining the value 2h cross square is 13 by 21 option 2, 4 by 21 option 3, 17 by 21 option 4, 3 by 7. Solution. Since L square operating on psi and LM is equals to LL plus 1 h cross square cat psi and LM. L square cat psi equals to 0 cat psi 200 plus 2h cross square bracket square root 3 by 7 cat psi 210 plus 4 square root 4 by 21 cat psi 311, obtaining the value 2h cross square is p bracket 2h cross square equals to summation of pi, where L equals to 1 equals to summation or coefficient I equal square equals to 3 by 7 plus 4 by 21 equals to 13 by 21, where state psi is normalized. So option 1 is correct. Question 10. The bond dissociation energy of a molecule is defined as the energy required to dissociate it. For hydrogen molecule and H2 plus molecule, the bond dissociation energies are 4.478 electron volt and 2.651 electron volt respectively. If the equilibrium bond lengths of both H2 and H2 plus are identical, the value of the ionization potential of hydrogen molecule will be closest to 1. 15-421 electron volt, option 2 11.773 electron volt, option 3 20.729 electron volt, option 4 6.471 electron volt. Solution. Write the reactions 4.478 electron volt plus H2 gives H plus H, reaction 1. Reaction 2, 2.651 electron volt plus H2 plus tends to H plus plus H. And for hydrogen atom, binding energy of the electron equals to 13.6 electron volt plus H gives H plus plus electron. To find the ionization potential of hydrogen molecule, adding the equation 1 and 3 while subtracting the equation 2, we get 4.478 electron volt plus 13.6 electron volt minus 2.651 electron volt plus H2 plus H minus H2 plus tends to 2H plus H plus plus E minus minus H minus H plus, which gives 15.427 electron volt plus H2. which gives H2 plus electron. Option 1 is correct. Question 11. A random walker takes a step of unit length towards right or left at any discrete time step, starting from x equals to 0 at time t equals to 0. It goes right to reach x equal to 1 at t equals to 1. Hereafter, if it repeats the direction taken in the previous step with probability p, the probability that it is again at x equals to 1 at t equals to 3 is option 1 1 minus p, option 2 1 minus p whole square, option 3 2p bracket 1 minus p, option 4 4p square 1 minus p. Solution. P is the probability of random walker when it repeats the direction taken in the previous step. You can see the figure. When random walker repeats the same direction in the previous direction, then its probability will be p, and where if it in opposite direction corresponding to previous steps, then it will be 1 minus p. Thus the probability capital P equals to small p bracket 1 minus p. One step is in the same direction as first step, previous step, and one is opposite direction, plus 1 minus p bracket 1 minus p, not in same as previous direction, which gives 1 minus p. Option 1 is correct. Question 12. The Hamiltonian of a particle of mass m is given by h equals to p square by 2m plus vx, with v of x equals to minus alpha x for x less than equals to 0, beta x for x greater than 0, where alpha beta are positive constants. The nth energy eigenvalues En obtained using WKB approximation is En power 3 by 2 equals to 3 by 2 square root h cross square by 2m pi bracket n minus half bracket close f function of alpha and beta, where n equals to 1, 2, 3 and so on. The function f alpha beta is option 1 square root alpha square beta square upon 2 bracket alpha square plus beta square, option 2 alpha beta upon alpha plus beta, option 3 alpha plus beta upon 4, option 4 half square root alpha square plus beta square by 2. Solution. According to WKB approximation, the quantization conditions 1 upon h cross integration over x1 to x2 p dx plus beta equals to n pi, where n equals to 1, 2, 3 and so on. You can see the figure. Note: for hard rigid potential wall beta equals to 0, and for non-rigid potential wall beta equals to pi by 4. Since the total energy E equals to p square by 2m plus v of x, and so momentum P equals to square root 2m bracket E minus v of x. Thus 1 upon h cross integration minus E upon alpha to 0 square root 2m E plus alpha x dx plus pi by 4 plus 1 upon h cross integration 0 to E upon beta square root 2m bracket E minus beta x dx plus pi by 4 equals to n pi. Further solving it, we get integration 0 E upon L alpha integration 0 to E upon beta square root 2m E minus beta x dx equals to pi bracket n minus half h cross. Taking the common square root 2m E and assuming alpha x upon E equals to t, then we get integration 0 to 1 upon alpha integration 1 minus t dt plus integration 0 1 upon beta square root 1 minus t dt equals to pi bracket n minus half h cross, which gives en 3 by 2 bracket 2 by 3 1 upon alpha plus 2 by 3 1 upon beta equals to square root h cross square by 2m pi bracket n minus 1 by 2. So option 2 is correct. Question 13. Using a normalized trial wave function psi of x equals to square root alpha e power minus alpha mod of x. Alpha is a positive real constant or a particle of mass m in the potential V of x equals to minus lambda delta x, where lambda is greater than 0. The estimated ground state energy is option 1 minus m lambda square by h cross square, option 2 m lambda square by h cross square, option 3 m lambda square on 2h cross square, option 4 minus m lambda square by 2h cross square. Solution. The Hamiltonian h equals to p square by 2m plus v of x equals to p square by 2m minus lambda delta x. Expectation value of h equal to energy equal to expectation value of h upon the inner product of states equals to alpha integration minus infinity to 0 exponential alpha x h exponential alpha x dx plus exponential minus alpha x h exponential minus alpha x dx. Since state is normalized, so inner product of states equals to 1. Energy E equals to 2 alpha 0 to infinity E or minus alpha x bracket minus h cross square by 2m d square by dx square bracket closed exponential minus alpha x dx minus alpha integration minus infinity to infinity lambda delta x exponential minus 2 alpha mod of x dx. E equals to 2 alpha exponential minus h cross square alpha square upon 2m bracket 1 upon 2 alpha bracket closed minus alpha lambda equals to minus h cross square alpha square by 2m minus alpha lambda. For ground state energy, d e function of alpha upon d alpha equals to 0. Alpha, we find alpha equals to minus m lambda upon h cross square. Thus, putting the value of alpha in equation 1, we get ground state energy E naught equals to minus m lambda square upon 2 h cross square. So option 4 is correct. Question 14. 5 classical spins are placed at the vertices of a regular pentagon. The Hamiltonian of the system is H equals to J summation or SISJ, where J is greater than 0, SI equals to plus minus 1, and the sum is over all possible nearest neighbor pairs. The degeneracy of the ground state is option 1 8, option 2 5, option 3 4, option 5 10. Solution. The Hamiltonian can be rewritten as H equals to J summation SISJ equals to J bracket S1 S2 plus S2 S3 plus S3 S4 plus S4 S5 plus S5 S3. You can see the figure. So making the table of the all possible combinations. So table 1, you can see the highest energy is 5J, which have degeneracy 2, and second highest energy equals to J, which has degeneracy 20, and the ground state energy equals to minus 3J, which have 10 possible combinations. So degeneracy is 10. So the ground state degeneracy is 10. Option 4 is correct. Question 15. The delta plus plus can be produced by colliding a pion beam onto a H2 target. In a reaction, pi plus plus P tends to delta plus plus tends to positive pion plus proton. In the rest frame of delta plus plus, the energy and momentum of the pion in the final state in mega electron volt are closest to. Assume C equals to 1 and mass of pion equal to 140 mega electron volt, mass of proton equal to 1 giga electron volt, mass of delta plus plus equal to 1 minus 1.2 giga electron volt. Option 1 210, 156. Option 2 230, 182. Option 3 175, 105. Option 4 190, 130. Solution. The reaction can be written as positive ion plus proton tends to delta plus plus, which again tends to positive ion plus proton. You can rewritten above reaction as delta plus plus tends to pion plus plus proton, which is equation same like A tends to B plus C. So write representation of Ford momentum of the above reaction. Ford momentum for delta equals to m delta c square upon c, 0, because it is in test frame or its momentum is 0, tends to momentum of phi in Fourier space equals to energy of phi upon c, spatial momentum p pi plus momentum of proton in Fourier space equals to rest mass energy of proton upon c, momentum of proton in spatial space. So you can rewritten as p delta minus p pi equals to p. Squaring both sides we get p square plus p pi square minus 2 p delta p pi equals to p small p square, which gives m delta square c square plus mass of pion c whole square minus 2 mass of delta c, energy of e pion upon c equals to mass of proton square c square. Solving this we get energy of pion equals to m delta square plus mass of pion square minus mass of proton square upon 2 m delta. Putting these values we get energy of e pion equals to 191 minus 5 mega electron volt. Now for momentum of the pion, E square equals to momentum of pi square c square plus mass of pion square c44. Putting these values we get 130.66 mega electron volt. So option 4 is correct. Question 16. An atom of mass m initially at rest resonantly absorbs a photon. It makes a transition from the ground state to an excited state and also gets a momentum kick. If the difference between the energies of the ground state and the excited state is h cross delta, the angular frequency of the absorbed photon is closest to. Option 1 delta bracket 1 plus 3 by 2 h cross delta upon mc square. Option 2 delta bracket 1 plus half h cross delta upon mc square. Option 3 delta 1 plus h cross delta upon mc square. Option 4 delta bracket 1 plus 2 h cross delta upon mc square. Solution: momentum of the photon, let P naught equals to h cross omega upon c. You can see the figure or representation in the figure. You can see clearly momentum of photon assumed as h cross omega upon c. Rest mass energy of the atom E naught equals to mc square. And when in excited states, its momentum is p and energy m star c square. According to question, the difference between excited state energy minus grounded state energy equals to h cross delta tends to m star minus m h cross delta upon c square 1. From conservation of momentum of initial condition equals to momentum in final condition tends to p equals to h cross omega upon c. From conservation of energy, h cross omega plus E naught equals to E star, which tends to h cross omega plus mc square equal to square root p square c square plus m star square c square c over 4. Further implies that h cross square omega square plus m square c over 4 plus 2mc square h cross omega equals to bracket h cross omega by c bracket close square c square plus m star square c over 4 bracket m star plus m bracket close bracket m star minus m equals to 2m h cross omega upon c square. Putting the value of m star from equation 1 and solving it, we get the angular frequency of observed photon equals to delta bracket 1 plus half h cross delta upon mc square. Option 2 is correct. Question 17. For a simple harmonic oscillator, the Lagrangian is given by L equals to half q dot square minus half q square. If h function of q and p is the Hamiltonian of the system and a function of p and q equals to 1 upon square root 2 bracket p plus iota q. The Poisson bracket a comma h is option 1 iota a, option 2 a star, option 3 minus iota a star, option 4 minus a minus iota a. Solution: the Hamiltonian can be written as h function of p q equal to summation of q dot I pi minus L. There is only single coordinate, so equals to q dot p minus L. Now p equals to del L upon del q dot, which gives momentum p equals to q dot. Therefore, Hamiltonian h equals to p square minus bracket p square by 2 minus q square by 2 equals to p square by 2 plus q square by 2. The Poisson bracket a comma h equals to del a upon del q del h upon del p minus del a upon del p minus del h upon del q equals to bracket iota upon square root 2 p minus bracket 1 upon square root 2 q. So the Poisson bracket a comma h equals to iota upon square root 2 bracket p plus iota q equals to iota a. So the option 1 is correct. Question 18. A linear molecule is modeled as two atoms of equal mass m placed at coordinates x1 and x2 connected by a spring constant k. The molecule is moving in one dimension under an additional external potential V function of x1 x2 half m omega naught square bracket x1 square plus x2 square. If one frequency of molecular vibration is omega naught, the other frequency is option 1 square root omega naught square minus km, option 2 square root omega naught square plus k by m, option 3 square root omega naught square plus 4k by m, option 4 square root omega naught square minus 2k by m. Solution: the Hamiltonian. H equals to kinetic energy plus potential energy equals to mx1 dot square by 2 plus mx2 dot square by 2 plus k by 2 bracket x2 minus x1 square, which is energy of spring, plus half m omega naught square plus x1 square plus x2 square. Now write circular equation mod v minus omega square t equals to 0, where t and v are matrices. Matrix t equals to del square k upon del x1 dot del x1 dot. It is double derivative of respective coordinates, which gives matrix 1 m0 0 m, and v equals to k plus m omega naught square minus k plus m omega naught square. Putting these values in circular equation, we get matrix k plus m omega naught square minus m omega square minus k plus m omega naught square minus m omega square. Solving this, we get the frequencies equals to omega naught and other frequencies square root omega naught square plus 2k by m. Option 3 is correct. Question 19. A particle of mass m is moving in a potential v function of r equals to minus k by r, where k is a positive constant. If L vector and P vector denotes the angular momentum and linear momentum respectively, the value of alpha for which vector A equals to L vector cross P vector plus alpha m k r cap is constant of motion is option 1 minus 2, option 2 minus 1, option 3 2, option 4 1. Solution. For central potential force F function of r equals to minus dv upon dr equals to minus k upon r square r cap, and the angular momentum is constant of motion. Vector L equals to m theta dot r square z cap, and derivative of L vector equals to r vector cross f vector equals to 0. If A vector is constant of motion, then derivative of A vector with respect to time equals to 0. Derivative with respect to time bracket L vector cross P vector plus alpha m k r cap equals to 0. Derivative of L vector cross P vector plus L vector cross derivative of P vector plus alpha m k derivative of r cap equals to 0. The unit vector r equals to cos theta I cap plus sin theta j cap, and unit vector theta cap equals to minus sin theta I cap plus cos theta j cap. Thus, derivative of unit vector r equals to theta dot theta cap, and derivative of theta cap equals to minus theta dot r cap, and force, which can be written as dp vector upon dt. Now from equation 1, the first term is equal to 0 plus bracket m r squared theta dot j cap bracket close cross bracket minus k upon r square r cap bracket close plus alpha m k theta dot theta cap equals to 0. From solving this, we get alpha equals to 1. Option 4 is correct. Question 20. The Debye temperature of a two-dimensional insulator is 150 K. The ratio of the heat required to raise its temperature from 1 K to 2 K and from 2 K to 3 K is option 1 7:19, option 2 3:13, option 3 1:1, option 4 3:5. Solution. The dispersion relation of a photon omega is proportional to K, where K is wave vector, tends to omega proportional to K over S, which gives S equals to 1, and the dimension of space D equals to 2. Thus the specific heat Cv proportional to T power D by S implies that C V proportional to t square. Now dq by dt equals to Cv implies that dq is proportional to integration t square dt. Thus the required ratio is q1k to 2k upon q2k to 3k equals to integration 1 to 2 t square dt upon integration 2 to 3 t square dt. Solving this we get 7 by 19. So option 1 is correct. Question 21. Rotational energy of a molecule in the angular momentum state J is given by Ej equals to h cross square upon 2I J plus 1, where I is the momentum of inertia of the molecule. The probability that the molecule will be in its ground state at temperature T such that kBT greater than h cross square by 2 is option 1 3 by 2 h cross square upon I kBT, option 2 2 by 3 h cross square upon I kBT, option 3 half h cross square I kBT, option 4 h cross square upon I kBT. The partition function of the system z equals to summation j equals to 0 to infinity gi exponential minus ej upon kBT, where gj is degeneracy of the state, equals to summation j equals to 0 to infinity 2j plus 1 exponential minus h square jj plus 1 upon 2 I kBT. The probability of ground state T when j equals to 0 equals to degeneracy of ground state equals to 1, so its probability equals to 1 upon j equals to h cross square upon 2 I kBT. You can see the integration. Question 22. A particle of unit mass and unit charge is moving in a magnetic field which varies as b vector function of r vector equals to b naught r vector upon r cube. B naught is a constant over a region far away from the origin if vector L is the instantaneous angular momentum of the particle within that region. Then derivative of L vector is option 1 2 b naught derivative of r vector upon r, option 2 minus b naught derivative of r vector upon r, option 3 b naught derivative of r vector upon r, option 4 0. Solution. The force on charge F vector equals to q velocity vector plus b vector equals to b naught upon r square r vector dot cross r cap. Derivative of L vector equals to r vector cross F vector equals to bracket b naught upon r square bracket vector r cross bracket r vector dot cross r cap. Further expanding the r vector cross r vector dot cross r cap in a cross b cross c, then we further rearranging it, we get b naught r vector dot upon r minus r dot r vector upon r square, which gives b naught derivative of d r vector upon r. Since r vector dot equals to velocity v is equals to r dot r cap plus r theta dot theta cap plus r sin theta phi dot phi cap. So option 3 is correct. Question 23. A uniform plane square sheet of mass m is centered at the origin of an inertial frame. The sheet is rotating about an axis passing through the origin. At an instant when all its vertices lies on x and y axes, the angular momentum is L vector equals to I naught omega naught bracket 2I cap plus j cap plus 2k cap, where I naught is the momentum of inertia about the x-axis. At this instant, the angular velocity of the sheet is option 1 2I plus j plus 2k omega naught, option 2 I cap plus j cap plus k cap omega naught, option 3 2I cap plus j cap omega naught, option 4 I cap plus j cap omega naught. Solution. The momentum of inertia matrix I cap can be written as this. You can see the figure. By symmetry, the moment of inertia about principal axis Iz z equals to Iz equals to Ix plus Iyy equals to I naught plus I naught equals to 2I. And momentum of product are 0. Now the angular velocity can be written as omega vector equals to omega x I cap plus omega y j cap plus omega z k cap. The angular momentum is L vector equals to I cap dot omega vector. Solving this and comparing the given values, we find the angular velocity omega vector equals to 2I cap plus j cap plus k cap omega naught. So option 2 is correct.